Welcome back. This is Mr. Greenstein's Geometry. We're in section 4.3, rotations, and this is part 2. We're going to talk about rotation postulate. So rotation, just like a translation and a reflection, is a rigid motion. So it's a congruent motion, which is an isometry. So anytime that you do a rotation, then we've done a rigid motion. That's a postulate. So let's take a look at, we have a case here, graph the composite. So we have 1, -3. 1, -3 is here. That's R. And then we have 2, -6, which is here, and that's S. We want to reflect about the y-axis. And then we want to rotate 90 degrees about the origin. So the reflection is this kind of rule. We take A, B, and that becomes -A, B. So if I was to do the reflection of 1, -3, then that becomes -1, -3. So -1, -3, and that becomes my R prime. Same thing with the S, 2, -6. It becomes -2, -6. So -2, 1, 2, 3, 4, 5, 6. So there's my S prime. So that's the reflection. And then the rotation, 90 degrees, if I have A, B, the rule is that it turns into -B, A. So let's take -1, -3, and then apply this rule, and it's going to flip them around and negate the y. So it's going to be 3, -1. So 3, 1, 2, 3, -1, and this becomes the new R double prime. And then we do the same thing with the -2, -6. We flip those around and we negate the B term or the y term, so it becomes 6, -2. So 1, 2, 3, 4, 5, 6, -2, and that becomes the S double prime. And that's 90 degrees. So then this becomes our final figure. That's the image that we create after doing the reflection and rotation. Rotational symmetry is a figure that can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. So if I was to take this figure here and then rotate it around this point, you can see that every 90 degrees it's going to map back onto itself. So I can actually rotate this and I have rotational symmetry. The center of symmetry is the point that we use for the rotation, which in this case is the yellow dot in the center. So that's the center of symmetry, and rotational symmetry means that we can map it back onto itself. This is not symmetrical, but when we go 90 degrees, it is symmetrical. 180 degrees, it's also symmetrical. And if we did it 270 degrees, it would also be symmetrical. What about each of these figures, rotational symmetry? Take a look at these at first and see if they have rotational symmetry. For A, you can do 180 degrees and we have rotational symmetry. So then that works. The octagon, you can do 45 degrees, 90 degrees, 135 degrees. So every 45 degrees, you have rotational symmetry because it maps onto itself. It looks exactly like the original. For the trapezoid, there's none. You have to rotate it all the way around to get to the same point again. So there's no rotational symmetry for this trapezoid. Now let's look at an application. The London Eye, which is an amazing Ferris wheel, is huge. Each one of those cars that you see there can hold 20 people. So it is amazing. And it has a radius of 67.5 meters and takes 30 minutes to make a complete rotation. If a car starts, so let's go to the next one, sorry. If a car starts at 67.50, what is the car's location after 7.5 minutes? Well, 7.5 minutes out of 30 is 1/4. So there's, if I divide 7.5 by 30, I get 1/4. So 1/4 around is where I'm trying to find. And 1/4 around is 90 degrees. So if I start out here, and then we'll call this point 67.5, 0. Then, oops, my 0 doesn't look like a 0. Then if it goes 1/4 around, then it's going to go 90 degrees. And 90 degrees rotation, if we look at the way that we map this, is AB becomes -B, A. So if AB is 67.5, 0, then we just map that and we get 0, 67.5. And that's our landing location right there. So this is going to be 0, 67.5. So we can actually use these rules to help solve problems. And we'll continue this conversation when we get back together in class tomorrow.